Hello. In this video, we'll talk about the parent or the library of parent functions. One of the goals of this video is to enable you to recognize the basic shapes of the graphs of different types of function. And these are commonly seen graphs or used graphs. We'll start off with the linear function. Because we know by looking at the equation. So when we speak of a parent function, we're talking about common graphs. Okay? So let's start off by looking at what we call linear functions. Okay? And for linear functions, the equation in slope-intercept form is y equal mx plus b, where we know that m is the slope and b, or 0 comma b, is what we call the y-intercept. So for example, y equals 2x plus 5. In this case here, m is equal to 2, and the y-intercept is the point 0 comma 5. Okay, the y-intercept is 0, 5. So if we look at the graph of this, and please make sure you remember for y in order for you to tell that the slope, so I'm going to make a note here, make sure the equation is in the form y equal mx plus b. If y is not by itself, then you cannot say the slope is the number next to x. Okay. So if we look at the equation here, and let's say here, and some point over here, I know that's 5 because that's the y-intercept. And this is the equation y is equal to 2x plus 5. Okay. So actually I want this to be between -1 and -2. So your graph should really pass through there, somewhere over there. And the equation So this is y equals 2x plus 5. Okay, m here, m is positive 2. Okay, so this is linear, right? Now, on the other hand, so you can see that the graph here is increasing. On the other hand, if we have an example, we have 3x plus 4y is equal to 12. Okay, so this is linear. This is linear. But the slope is not 3. Okay, to find the slope, to identify the slope, we must solve for y. So if we have 3x plus 4y is equal to 12, the first thing we will do is minus 3x on both sides. And that will leave me with 4y is equal to minus 3x plus 12. And then to get y by itself, we will divide each term by 4. Okay. And if I do that, I will have y is equal to minus 3 over 4x plus 3. Now we can now tell the slope and y-intercept. So now the slope m, okay, m is equal to negative 3 over 4, and y-intercept is 0, 3. So if I graph this, so since my slope is decreasing, I know that my line is going to be going this way. And here we know that m is minus 3 over 4, right? And the y-intercept here is 0, 3. This is the point 0, 3. That's your y-intercept. So remember, this is called the rise, and this here is called the run, because slope is the same as the rise over the run. Right? So slope is rise over run. Now, if we look at another example, and you're asked to graph y equals 5. Well, anytime we have a function in the form y equals a constant, okay, anytime we have an equation y equals a constant, that will be a horizontal line. So this here is a constant, this is the constant or an integer. Okay. So y equals 5. Let's say this is the point 5. My line will be passing through that horizontal line, passing through the point 5. And this is the line y equals 5. Okay. Over here, I didn't write, my equation is 3x plus 4y equals 12. You should always get into the habit of writing the equation next to your line. So the slope, okay, note, slope, which is m, for any horizontal line is 0. Because the slope measures the steepness of the line, how steep the line is. So the slope is 0 for any horizontal line. Doesn't matter what it is. If we look at another example now, if we have x equals 3. Well, notice now it's not x, it's not y, it's x. When it's y equal, it passes through the y-axis. When it's x equal, it will pass through the x-axis. But because it's in the form x equals, now we are speaking of a vertical line. A vertical line. Okay. So let's say here is the point 3. It will be a vertical line passing through that point 3. Yeah, a vertical line. And this will be x equals 3. Now, the slope m here is equal to undefined. Okay. M here is 0. The slope of any vertical line is undefined. The slope of any vertical line is undefined. So you're familiar, or should have been familiar, with most of the linear functions, right? We're looking at linear. Now, so this here is in the form y equal mx plus b, where we have a slope and some specific y-intercept. So here's an example of that. The slope could be positive, the slope could be negative. We have horizontal line where the slope is 0. We have vertical line where the slope is undefined. Now, for the common parent functions, let's start off by looking at the identity function. The identity function. Yeah. The identity function, this is a linear function. This is a linear function. In the form y equal mx plus b, but the y-intercept, which is really b, is 0. Okay, so if b is 0, we're left with y equal mx. Okay, and this is your identity function. Now for the identity function, the slope for the identity function is 1. So that means y equals x is what we have, the identity function. Makes sense, right? Identity, it's identical if x is 1, y is 1, if x is 2, y is 2, and so forth, right? So it's identical values. Now, if we look at the graph of the identity function, okay, if we look at the graph, if b is 0, that means the graph must pass through there. So your identity function is this graph. So this is y equals x. So if this is 1, this has to be 1. If this is 2, this has to be 2. If this is minus 1, this has to be minus 1. If this is minus 2, then this point here has to be minus 2, and so forth, right? So what are some of the characteristics of the identity function? Notice that the y-intercept is 0, 0. The slope m is equal to 1. Okay. Also, you should notice that the domain is minus infinity to infinity. So remember, domain is the set of acceptable x values. Okay. So by looking at the graph, you can see that there's going to be a value here, there's going to be one here. No matter where on the x-axis you go, there is a corresponding y value. So we do have a video on how to find domain and range. We talked about that. So if you want to refresh in that, please look at that video. Okay. Now from the identity function, so also here, if we want, so the domain, right, let's just make a note of that. The domain is minus infinity to infinity, and the range, and let's write that, the domain minus infinity to infinity, and the range is also minus infinity to infinity. So for any linear function, except the two special cases, the vertical and the horizontal line, for any graph in the form y equal mx plus b, the domain and range will always be minus infinity to infinity. Okay. Now, why is the identity function such an important function? Well, from the identity function, okay, by what we call transformation, by moving this function here, if we can push it upward or pull it downward or move it to the left or move it to the right, we are able to create an infinite amount of other functions. Okay. So what I'm saying here is by transformation, okay, by transformation, it just means moving, okay, the graph up, down, right, or left, okay, right or left, we can create an infinite amount of other graphs. Okay. And what do I mean by that? Well, here is the identity function. Okay. Here is the identity function. Here we have y equals x. Now, if we move this graph upward, okay, we can get this graph. If we move this point here, this point, which is on the graph, okay, if we shift that point here, then we can have a graph that looks like this. Okay, and this is now in the form y equal mx plus b. Or if we move it downward, okay, if we move it downward, we can have a graph that looks like this. So all we're doing is taking that point on the graph, that dot, which is at the origin right now, okay? And if we now move it here, now if I move it there, you will see that my graph would look something like this, which is in the form y equal mx plus b. So here is the b right now, okay? Here is our b, okay? Or if I move it, if I move to the left, okay? If I move it to the left, so now that dot becomes here. And my identity function will now look like this. Okay. And this is also in the form y equal to mx plus b. So by moving this point, right, we're moving this point here, okay, this point here, that point's become there, which is here, which is here. We're able to get an infinite amount of graphs from this graph, okay? So the identity function is a very, very important function for us, extremely important. We're able to move it around. And that's very, very unique for us, extremely unique. So in this chapter, we have a bunch of functions that we would like to look at. I'll use variety of functions, okay? So those are called our parent function. Yeah. So we have a list, okay? We have a list of common functions. And those are called the parent functions. Yeah, we call them the parent functions. Yeah. So let's look at that list. So here's the list of the commonly function. So most commonly used graphs in algebra. Okay. So we've basically looked at this one here, and we've looked at that one there, right? So we'll look at a few of them in detail. I wouldn't go through all of them, okay? We'll look at a few of them in detail now, and then see what are some of the characteristics of them. Okay? So please make sure you become familiar. So I suggest you become familiar with these graphs and their shapes. Okay. So we want to make sure we become very familiar with these graphs and what the shape look like. So if I ask you about the identity function, you should know that the identity function is this one here, right? The y-intercept is 0, 0. If I ask you about the constant function, you should know about the constant function can be this one here, okay? So let's just go through some of them. The next one I'll talk about is the squaring function. So we'll look at this one here now, the squaring function. And if we look at the squaring function, okay, the squaring function is also known as the parabola. So the graph of this is called a parabola. Okay, so it is a U-shaped sort of looking graph. It's U-shaped, okay? And the characteristics is, if we write out some of them, the domain is minus infinity to infinity. That's our domain. The range is 0 to infinity. Okay. So here are some of the characteristics. The set of all real numbers, that's the domain. All real numbers mean minus infinity to infinity. Okay. The range are all non-negative real numbers. So that's 0 to infinity as interval notation. We do have a video where we talk about even functions. Okay, the graph has an intercept of 0, 0. It's increasing or decreasing. So it's decreasing from minus infinity to 0 and increasing from 0 to infinity. The graph is symmetric, meaning that this side, okay, is the same shape as this side. Okay. So these are some of the things that you should know as you look at these graphs. Okay. So this is what we call the squaring function. We also have what is called the cubic function. So we have the cubic function, okay? And the cubic function looks sort of this here, okay? It's cubic. So here we can say that the domain is from minus infinity to infinity now, because all x values. The range is also minus infinity to infinity. Okay. The function is odd, meaning there's symmetry at the origin. It has a x-intercept at 0, 0 and a y-intercept at 0, 0. And it's increasing consistently. Okay. So these are the characteristics of the cubic function. Okay. Cubic function. And there are many different other graphs here. Okay. We'll talk about the square root function. Okay. So let's continue. Okay. So here we have the square root function. Okay. Now notice that your domain here, the domain is including 0 to infinity. It starts from here and it travels along all the way. Remember, it doesn't end, right? It does not end. So that's why it goes to infinity. The range would also be 0 to infinity. Yeah. there is an x-intercept at the origin, and the graph is also increasing. The graph is increasing. So just some of them, I wouldn't go through the entire list, okay? So what have we done so far? We've looked at this, we did the square, we did cube, we did mx plus b, we did square root. Let's just do one or two more. I will talk about the greatest integer function. The greatest integer function, very important function. Okay. So let's see what else we can look at. Yeah. Okay. Looking at the reciprocal function now. So the reciprocal function is just 1 over x. Okay. We'll see here that the domain of this is very unique because x cannot be 0, right? X cannot be equal to 0. So the domain here would be from minus infinity to 0, and then union from 0 to infinity, because we have to exclude 0. And notice that the range happens to be the same. So the range would also be minus infinity to 0 to 0, union that with 0 to infinity. Okay. This is an odd function because there is origin symmetry. The graph is decreasing from minus infinity, it's going down to 0. And then it's also increasing from 0 to positive infinity. Okay. Now there's also the reciprocal 1 over x squared, so you should look at that. Okay. So keep in mind, under the same family of reciprocal, we also have f of x equals 1 over x squared. And let's just draw that one in, because I find this one here to be very common also, but it's not under the list. Yeah. For 1 over x squared, we're going to have a graph that looks like this. Because anytime x is negative or positive and you square it, the answer will always be positive. So the domain here, the domain is very similar. It's minus infinity to 0, right? Because notice x cannot be equal to 0. Union that with 0 to infinity. And the range will only be from 0, not including 0 to infinity. Okay. The graph is increasing. Okay. It is increasing from negative infinity to 0, and it's decreasing from 0 to negative infinity. Yeah. There is y-axis symmetry. So this is one that's not on the list. I don't think it is, but let's look back. Yeah, I don't see that on the list of commonly used, but you should know that, okay? And let's look at one more, the reciprocal function. Oh, sorry, the greatest integer function, okay? The greatest integer function, also known as the step function, okay? So we have the step function. Okay, and we call that also the greatest integer function. Okay. The step function or the so here is the step function, also known as the greatest integer function. Okay, so you'll notice that the domain here is, although the graph is in pieces, the domain is all real numbers, right? So the domain is from minus infinity to infinity, okay? Because if you start out, remember that graph continues here. For here, there's an x value. Here, there's an x. Even here, it hits this one. There is also an x value there, okay? So for every single x values, you will get some sort of, the domain exists for every single x values, okay? So now the range is not the case, because the range only exists for every integer, okay? And that's why we say here that the range, okay, is a set of all integers. There is a y-intercept at 0, 1, okay? The graph is constant, so notice that. Now, why is this important? Well, the greatest integer function, and especially if you do, if you're a computer science major, sometimes you will hear of something called the floor function and the ceiling function. And what happens is that for the ceiling function, okay, these dots here, the open circles, just shows on the other side, okay? So you will have a function or a graph that now looks like this. Okay, this is called the ceiling function. And it's referred to the ceiling function because if you have to take a value, you take the higher value. So for example, your cell phone, right? If you look at your cell phone, the itemized bill, if you speak to someone for 1 minute and 30 seconds, okay, or 31 seconds or 29 seconds, they round that up. Once it's over 1 minute, they round it up to 2 minutes. They don't write you speak to someone for 1 minute and 38 seconds. They round it up to the next number, okay? And that's why it's called a ceiling, because they go to the higher number. There are some functions out there where they will take the lower number, and that's called a floor function. So these are just some of the common functions that you will hear about, you know, as you talk about algebra. Yeah. So the ceiling and the floor function is very common in computer science majors, especially when you have to write, if you have to write a program. Last thing we want to talk about today is how do we graph what is called piecewise functions, okay? So we also want to look at piecewise functions. And a piecewise function is a function that's made up of different pieces of other functions. So this is, you can think of this, we can think of this as a function that is made up of various parts or various parts slash pieces of different graphs. For example, if we have the identity function, okay, the identity function looks like this: y equals x. If we have the parabola which we know looks like this. Yeah, y equals x squared. Now let's say that I want to make up a graph and I only want this piece of this graph. Okay, and I want to make up a graph where I only want this piece of the graph. So if I take the two highlighted, if we take the two pieces, yeah, we now have a new graph. And that graph slash function, we can call that f of x is equal to x, and here x is less than 0. And then we also have the graph x squared for x greater than or equal to 0. And this here is my piecewise function, f of x. Okay, so it's made up of two pieces, yeah, for this particular function. So the question is, how do we graph it? Well, to graph it, yeah, to graph, we make a table of values for each piece. Okay, so this is our piecewise function. This is what we call the piecewise. Okay, there's our piece, this piece, and this piece here. Now, please note that in a piecewise function, if this is less than 0, this will be greater than or equal to. Both of them cannot contain the equal sign. Okay, so I would suggest to graph this, we can create a table of values for each piece. Yeah? Meaning, if I want to graph the function x, when I create my table of values, okay, when I create my table of values, these values here has to be less than 0. Okay, so we can use things or values such as -1, -2, -3. You can even go up to -0.5 or -1/4, -0.25. Okay, but you cannot choose 0. So if this is x and this is y, then the values will be the same. Okay. And then for the other function, y equals x squared, when you create your table of values for this graph, right? These values here will be values, okay? These values will be greater than or equal to 0. So here we have 0, 1, 2, 3, 4, and so on. And if I fill in those values, 0 squared, 0, 1, 4, 9, 16. So in order to graph this now, if I have to graph this, okay, if I want to graph it, I know that at -1, it's -1. At -2, it's -2. At -3, it's -3. These are the points that I'm plotting. So if I connect, now remember, 0 is not included. Here, 0 is not included. Okay, so we put a hole at 0, and my graph now goes this way. Okay, that's my graph. And for my next graph now, 0 is included. Okay, 0 is included, and I do 0, 0, 0, 0, which will be here, then 1, 1, which is here, then 2, 4, which is here. So you'll notice that I'm getting that piece of my parabola. And this entire graph is the graph, the piecewise function. This is f of x equals x for x less than 0 and x squared for x greater than or equal to 0. Okay. Now you have to be careful, because if I ask you to evaluate f of, let's say, -1, you have to know where to plug it in. So -1 is here. So you have to plug it in this graph, which is x. So f of -1, okay, f of -1 will be -1. We have to use, so we must use the piece f or y equals x. Yeah. And that's because x is where the value is less than 0. If I ask you to evaluate f of 3, okay, here we must use the piece y equals x squared, because this function here, x is greater than or equal to 0. This function here, x is less than 0. So f of 3 will be 3 squared, which is equal to 9. Okay. So, you know, as always, you guys need to practice more. Okay, I would strongly recommend you practice more examples of this. And be very familiar with also piecewise functions, because in today's world, we take pieces of different things and we create our own, right? So we are using piecewise functions all the time. So please practice as many examples as possible and become very familiar with these functions and the topic.